Thank you. Thank you so much for the lovely introduction, and thank you for inviting me. Hopefully you can see my screen. There's a little comic over here making a little bit of fun of our paper, mainly because we improved some number very, very slightly. So I'm going to talk to you about that number. Can you see the pointer? Yeah, okay, good. All right. So as I said, I'm going to talk about matrix multiplication. Hopefully I can move the slides. Okay, so it's working. Great. So what is matrix multiplication? We all know and love this operation. You're given two n by n matrices. Today, let's assume they're real numbered entries. And you want to compute another matrix, which is also an n by n matrix with this definition over here. The sum over k of aik plus bkj is in the ij entry. Matrix multiplication has been defined many centuries ago. And for us, it's interesting to know how fast we can compute the product of two matrices. And here we're going to ignore how large the entries are going to be in the matrices. So we're going to assume that operations over two entries in our underlying field, like over the real numbers, will take constant time. So things like products and additions, subtractions, and divisions over the reals will take constant time. And what we want to know is, given two n by n matrices, how many operations over the field, over the reals, do we need to get the output matrix C? And for n by n matrices, we say that the number of operations is like n to the omega plus little o of 1. Omega is like the smallest real number for which you can get this many operations. Omega is at least 2 because you need to output the output matrix. So you need at least n squared operations here. And is at most 3 just because of the definition. From the definition, you can see you can do it with n cubed operations. So then the question is, where between 2 and 3 omega lies? Of course, I don't really need to introduce matrix multiplication for you, why we need to study it. It has so many applications. Most linear algebraic operations can be reduced to matrix multiplication. Graph algorithms can be improved by using matrix multiplication just as a black box. You know, this black box over here. And so on. There's like many applications, and which is why we actually care about the problem. So this is one reason to study it. Of course, I study because I find it like a fun problem to think about. All right, so here's a little graphic of the matrix multiplication exponent over the years, what we know about it. So up until 1969, omega, like the naive algorithm, was the best. So omega was basically 3. In fact, people thought that this is probably the best possible. And Strassen actually showed that it is not the best possible. You can actually get 2.81. And then Pan got something better, a little bit less than 2.8. And there was a little bit an improvement after that with new techniques. Schoenhagen brought it down almost to 2.5. Strassen brought it down to less than 2.5 over here. Coppersmith and Winograd brought it down to 2.376. And then there was a long standstill until Andrew Stodders in his PhD thesis showed that actually 2.376 can be improved a tiny bit to 2.374, and then I got a tiny improvement after that. Legao got another tiny improvement, and we got an even tinier improvement. So let's see what the improvements are. N cubed, n to the 2.1. Coppersmith and Winograd was actually 2.37548. Stodders got 2.37369. I got 2.37288, which is now less than 2.373. Legao made the 8 into a 7. We made the 7 into a 6. It's a big deal. Yeah. Okay, so let's talk about this. There's a reason why we're kind of stuck over here, and there's some work on why this is happening, but this is not what I'm going to talk to you about today. Today, I'm going to talk to you about how to get from 7 to 6. All right. So here's my plan. Actually, the majority of this talk will be an introduction to matrix multiplication algorithms, because there's a lot of language I need to introduce in order to get to what we're doing. An introduction to something called the laser method, which is the method that has been used in the last several decades for matrix multiplication algorithms. Then I'm going to talk about it the last 5-10 minutes. I'll talk about what we actually do. But in order to get there, I need to get through here. Okay, so let's begin. Here's matrix multiplication. We want to figure out what omega is, but what is this question actually asking? So it's actually talking about, it's a question about the asymptotic rank of the matrix multiplication tensor. So I need to define the matrix multiplication tensor. I need to say what asymptotic rank is. All right, so let's do that. What are tensors? Tensors have many guises. Okay, they can be like order 3 tensors could be viewed as hypermatrices, so with entries from an underlying field like this, or they can be viewed as bilinear maps. So you take 2 vectors from the field and you output another one. Or they can be thought of as trilinear maps. You take 3 vectors and you output a scalar. Or they can be viewed as multilinear polynomials. And I'm going to take this third view, okay? So it just makes the most sense. It's the simplest way to talk about them. Okay, so here's what I think of as a tensor. So you have 3 sets of variables. The x variables, n of them, the y variables, m of them, and the z variables, there's p of them, okay? They're formal variables. A tensor over these variable sets is just a trilinear polynomial, like this, is defined by the coefficients alpha I, j, k, which are in front of the term xi times y, j times zk. And these terms over here, they're just elements from the field. All right, so this is our tensor, just a trilinear polynomial over these variables. Now, what does that have to do with computational problems? Well, any fixed polynomial like this corresponds to some computational problem, which is given the vectors x and y, for every z sub k, compute the coefficient in front of z sub k in this polynomial, okay? So z sub k, those guys here, they're the output variables, and the x's and y's are the inputs, and you want to compute this polynomial in front of z sub k for every z sub k. So this is just, you're computing a set of polynomials. All right, so here, with this in mind, here's the matrix multiplication tensor. So what is this? It's very symmetric. The sum over I, j, k. This is the matrix multiplication tensor for multiplying an m by s by an s by t matrix. It's very symmetric. And if you look at the coefficient in front of the entry z sub ki, it is exactly the ik entry of the product of the matrices x and y, right? Why I wrote ki here and not ik? That's because it's like nice and like has a rotational symmetry that's actually useful. But if you look at z sub ki, is just its coefficient is the x times y ik entry. All right, so this is matrix multiplication. Now the question about the complexity of matrix multiplication is just about the asymptotic rank of this tensor over here as n grows. So now I have to tell you what rank is and what asymptotic rank is. All right, tensor rank. It's just a measure of the complexity of a tensor. And in order to define tensor rank, let's define what a rank 1 tensor is. So tensor T, which is a multilinear polynomial, has rank 1 if there are these vectors with entries in the field, A, B, and C, okay? So that you can express the tensor as a product of a linear combination of your x variables with these coefficients from A times the linear combination of the y variables times the linear combination of the z variables. When you write it out, it looks like the tensor, its coefficients over here are ai times bj times ck for each ijk. Often we write it like this: A tensor B tensor C. This is what a rank 1 tensor is. Okay. The rank of a tensor is just the minimum number of rank 1 tensors whose sum equals the tensor. Okay. And this is just a natural extension of matrix rank, if you think about it. Then you wouldn't have this third term here, and you just put like this times this, and then it will be A tensor B will be a rank 1 matrix. But here we have 3 terms, and it looks like this. Okay, good. So this is tensor rank. Here's a matrix multiplication tensor for m by s by s by t. And we care about tensor rank because if we have a bound on the rank of an m by s by s by t tensor, and let's say it's r, then we immediately get a bound on omega. We get that the omega is at most 3 times log base MST of R. And the way it works is a recursive algorithm, which I'll give you in a second. And if M equals S equals T, then this 3 can go away. So the point is, as long as we can bound the rank of a fixed size matrix multiplication tensor, we immediately get an algorithm for multiplying arbitrary matrices. So here's how it works. So what does it mean for this tensor, the matrix multiplication tensor, to have rank R? It means that it's a sum of R ranked 1 tensors, which look like this. So linear combination of the x variables, linear combination of the y variables times a linear combination of the z variables. All right, so this I claim immediately gives us an algorithm. So what is the algorithm? You take arbitrary size matrices. These are n by n, okay? And this over here is talking about m times s by t matrices, where m, s, and t are constants, and n here is allowed to grow. So think of m equals x equals t equals 2. So 2 by 2 by 2. So then what you do is, this is what Strassen did. You take your matrices, which are really huge, and you view them as 2 by 2 matrices, where the entries are actually blocks of the same size, n over 2 by n over 2. For m by s and s by t, here you would consider the matrix as an m by s matrix where its entries are blocks of size n over m by n over s. And the same with this one, and all the same with the output. And what you do now that you think of these matrices as block matrices, right? They're constant size matrices, but the entries are huge. You look at this decomposition and you say, well, this decomposition says that I can get the following algorithm. For every choice of L from 1 to R, I look at this product of this linear combination of the x variables times this linear combination of the y variables. Now, these x variables for us are just submatrices, so blocks. So what it's saying is sum up a bunch of these blocks with some coefficients, which takes linear time in the size of the matrix, because summing and multiplying is summing matrices takes linear time in their size, so this is very cheap to do. The same over here, you take a linear combination of the y blocks, okay? And then you multiply them recursively. You do exactly the same thing on these brand new matrices. And then you look up what the coefficient should be in front of the zki. Well, it's just a linear combination with these coefficients of the products that you computed. And again, linear combinations of matrices, again, n squared time, like linear time in the size of the matrix. So this gives us a recursive algorithm. Any rank decomposition of a constant size matrix multiplication tensor gives us a recursive algorithm for multiplying arbitrary matrices. And you will say, well, what if this is a rectangular thing and you want to multiply square matrices, the recursion won't work out? Well, like in the second time you switch the order, instead of MST, then you do STM. This is why it's nice that it's symmetric, okay? Right. Anyway, it's just on the side. So this is how rank corresponds to algorithms. Hopefully this is okay. Any questions? Okay, good. So Strassen in 1969 looked at the 2 by 2 by 2 matrix multiplication tensor. He showed that the rank is actually 7. And this in turn showed by this lemma that the omega is at most log base 2 of 7, which is 2.81, which is great. So what happened is that Strassen did this, and then Pan said, well, look, I can give a rank bound for 70 by 70 matrices. It's a really big number. And then if you work it out, you get something that's smaller than 2.81. It's actually less than 2.8. So, but then 70 by 70 looks kind of big, and it became infeasible to think about larger and larger matrices by hand. So what happened after that is, people started looking at indirect approaches. So instead of picking a fixed size matrix multiplication tensor and figuring out what the rank should be, they looked at fixed size other tensors and figured out what their rank should be and related that to matrix multiplication. Okay, so here's a big slide on how matrix multiplication algorithms are designed. As I said, Strassen began with 2 by 2 matrix multiplication using only 7 multiplication, namely the rank is at most 7, and used the simple recursive approach. And a lot of stuff happened, which I'll touch upon in a little bit. And then Coppersmith and Winograd defined this Coppersmith-Winograd tensor, and that tensor squared, whatever that means. And then they used something called the laser method, which I'll discuss later. Stodders used the next power of this tensor, use the laser method. I used the 8th power, use the laser method. Legal used the 32nd power and use the laser method. We use the 32nd power, but we use a different method. So slightly improved laser method. So the difference here is that while we can use exactly the same tensor, but with the new method, we get better bounds. So I'm going to talk about how the method changed today. Okay. So what is the laser method? As I said, it's an indirect method for designing matrix multiplication algorithms. It was developed by Strassen, who also came up with the name. It's unclear to me exactly how it corresponds to what's going on, but he had something in mind. And then it was optimized for the Coppersmith-Winograd tensor by Coppersmith and Winograd, and many other tensors as well. So in fact, Josh, who is now a professor at Columbia, he showed in 2019 that there's a large class of tensors, which you can define those tensors for which the laser method applies, whatever that means. For those tensors, if you can achieve omega equals 2 with them, then you can also do it with the laser method. So in a sense, this method is universal for a certain class of tensors. Okay, so indirect approaches. What are they all? I'm going to have 2 ways of looking at them. So let's say, first, what you do is you take a different algebraic problem, which is not matrix multiplication, but something maybe simpler looking. And you have a very efficient algorithm for it, which means that you have a good rank bound. And then you show how to reduce matrix multiplication to that algebraic problem, in the sense that you can use the fast algorithm for that algebraic problem to solve matrix multiplication faster. So these algebraic problems are just, you've got to evaluate a set of polynomials. So for example, matrix multiplication for 2 by 2 matrices computes these 4 polynomials. But instead of looking at 2 by 2 matrix multiplication, maybe you look at this problem P, which has more variables. Maybe it has 5x variables, 5y variables, and maybe it has 5 output variables, 5 polynomials you need to compute. And let's say somehow you got a very fast way to evaluate these polynomials. So the way you would evaluate matrix multiplication instead is you're going to remove some of the inputs and some of the outputs, and you'll get matrix multiplication out of it. So for example, if I remove these 2 and I remove, this will remove this term over here. And if I remove this output over here, basically I say I don't care about that output, then what I get is exactly matrix multiplication, 2 by 2 matrix multiplication. let me give you a second view of what I just said in terms of tensors. We have the 2x2 matrix multiplication tensor, and in the tensor notation, the previous problem I just showed you looks like this. So it has these 5 output variables and 5x variables and 5y variables. And the way to get 2x2 matrix multiplication from this is to set variables to 0. So what you're going to do is you're going to set some of the x variables, some of the y variables, and some of the z variables to 0, and you'll get exactly this trilinear polynomial. So I'll set these guys to 0. I get z3 to 0, which will remove this term, and I get exactly matrix multiplication. Okay, so this is called a zeroing out. So you're zeroing out the tensor P to get 2x2 matrix multiplication. And let's say I define it like this. 2x2 matrix multiplication is a zeroing out of the tensor P. Here's a simple lemma. If Q, a tensor Q, is a zeroing out of P, so I zero out some variables of P and I get Q, then the rank of Q is at most the rank of P. That's pretty simple because I just zero out the variables in the rank decomposition and the rank doesn't increase, stays the same. So if I can get a very good rank bound on P and I happen to get that MST, the matrix multiplication tensor, M by S by S by T, can be zero out from P, then I also get a bound on omega. Right? Very, very simple. So it's a reduction from matrix multiplication to potentially larger looking tensors where you get to zero out some variables and you get bounds. Okay, so it gives us more freedom. All right, so here's again the laser method. So actually it's a method to reduce direct sums, which I have to define, of matrix multiplication tensors, to actually powers of tensors via zeroing out. And these tensors have to have special structure. So it's a very special way to zero out things. So I'm going to define all these things. I'll define the direct sums, I'll define powers, and I'll define the special structure. So here's the idea. So the arrows mean reduction in terms of algorithmic reductions, right? So let's say I want to compute the product of n by n matrices. Then Schoenhagen showed that you can take an algorithm for computing a direct sum. This is what this means, of a bunch of matrix multiplication tensors of different dimensions. And you can reduce the n by n matrix multiplication problem to this new problem, which I have to define. Then there's also a different way, with a different part, which says that I can take the tensor power of a tensor, which is a very huge tensor, and I can reduce its rank computation or its rank bounding to just reducing the upper bounding the rank of a tensor T. So if I can upper bound the tensor T, then I can upper bound its nth power. And then finally, the laser method relates these two. It reduces computing this sort of problem to computing the nth power of some tensor, but the tensor T has to have special structure. So I'm going to look at this first, then this, and then finally this part. Let's look at this first. I need to define direct sum. So first, what is the sum of two tensors? So look at this tensor T. It's x1, y1, z1 plus x1, y2, z2. I get to rename the variables. So for example, x2, y2, z2 plus x2, y3, z3 is the same tensor as this one. We're just renaming the variables. So is this. This is the same tensor. So a sum of two copies of T could look like this. And I get to these two copies could share variables. A direct sum of two copies of T is not allowed to share variables. So it's basically two copies of tensor T whose variable sets are completely disjoint. So for example, a direct sum of matrix multiplication tensors are a bunch of completely independent matrix multiplication problems. So they don't share any variables. So intuitively, you shouldn't be gaining anything from solving them together, but it turns out it can still gain something. So So this is a direct sum, a bunch of the sum of a bunch of tensors that do not share variables. All right, so Schoenhage showed that if you can upper bound the rank of a direct sum of many matrix multiplication tensors, you can also bound omega. In particular, this is a bit simplified. He showed something more complicated. So if you can get the direct sum of k copies of the same matrix multiplication tensor has rank at most r, then when you bound omega, you get to divide this rank by k, by the number of copies in the bound. So it's as if you're getting, you're getting to average out the rank over all these copies, even though your rank is only for computing their sum, the direct sum. So, all right. So this is actually interesting because it turns out that sometimes you can get a better bound on the rank for a direct sum of stuff than by computing them individually. And because of this, this is actually useful. It's actually surprising that you can get a better bound for the sum than the sum of the ranks. Okay, so this is what we use from Schoenhage. We use that if we can get a rank for the sum of a direct sum of a bunch of matrix multiplication tensors, or let's say they have the same dimensions, then you get to bound omega by 3 log base mst of r over k, where mst are the dimensions of the matrix tensor. Okay, so this is basically this part over here. So if you bound the rank of this thing by r, then you get a bound on omega by taking the 3 log base, the product of the dimensions of r over k, where k is the number of things. All right, the next step is over here. I'll define the Kronecker product of two tensors. So let's say we're given two tensors, which we know are multilinear polynomial. The Kronecker product is just the product of the two polynomials. All right, so you multiply the two polynomials. However, you identify the pairs of x variables to be a new variable. So the Kronecker product of S and T is a tensor whose variables are pairs of x variables, pairs of y variables, and pairs of z variables. And the coefficient is just the natural coefficient you will get by multiplying the two polynomials. Okay, that's the Kronecker product. The tensor power, the Kronecker tensor power of T, is just multiplying T by itself n times that power. Oh yeah, and before this, I want to point out that when you take the nth power, the variable sets are now n tuples of the original variables. So originally, let's say we had the x variables, now we have n tuples. And same with the y's and the z's. Here's a lemma for matrix multiplication, because matrix multiplication has very special structure. If you take the Kronecker product of a matrix multiplication tensor with another matrix multiplication tensor, you get a new matrix multiplication tensor whose products are just whose dimensions are the products of the dimensions. And this just corresponds to that blocking idea that I told you before. If you can consider a matrix, n by n matrix, as a 2 by 2 matrix of blocks of size n over 2 by n over 2. And that's basically saying that n by n matrix multiplication, you can view it as like a 2 by 2 by 2 times a n over 2 by n over 2 by n over 2 matrix multiplication. All right. Again, a simple lemma, because Kronecker products are just essentially products of polynomials, is that the rank of S times T is bounded by the product of the ranks of S and T. All right, so that's very easy. Now, the rank of the nth power of a tensor is at most the nth power of the rank of the tensor. But it turns out that sometimes the rank of the nth power can be much less than the nth power of the rank of the tensor. And this leads to the definition of asymptotic rank. So if you take a tensor T and you take the limit Actually, the limit is well defined. So you take the limit as n goes to infinity of the rank of the nth power to the 1 over nth power. Okay. And it turns out that this can be much smaller than the rank itself. And you can see this, for example, with the matrix multiplication tensor. We know that for 2 by 2 matrix multiplication, the rank for that tensor is 7. But the asymptotic rank of matrix multiplication itself is much, of 2 by 2, is much less than log base 2 of 7, is 2.373, right? So you can get much smaller bounds. So because of this, when we work with matrix multiplication algorithms, we actually want a bound on asymptotic rank, because then we would get better bounds on omega. Okay. Questions up to this point?
So can I have a question about the previous slide about this Schoenhager results?
Sure.
So is it a good like intuitive interpretation that that you don't get anything by computing many products? Like if you somehow magically had an algorithm that could fast compute 5 matrix products, then it must mean that you can compute a single one in 1/5 of the time.
So it doesn't mean that you can compute a single one 1/5 of the time, but remember omega, you get to take big powers.
Mm-hmm.
Right? And so in the big powers, you can actually divide by k in the big power. Intuitively, the way that thing works is you take your tensor, which is the sum of matrix multiplication tensor, you take a huge power, now it blows up. And then you show that you can zero out a bunch of variables so that what remains is actually matrix multiplication of the correct dimensions. And it actually turns out that you can divide the rank by k when you do that. It's as if you had, a single one with the division by k.
Okay, so this is how the proof goes.
Mm-hmm.
Okay. Okay, thanks.
Okay, is that okay?
Yeah, for me, yeah.
Okay, great. Any other questions?
So I have a question, like,
Yeah.
is like, maybe this is a dumb question, but if we have this asymptotic rank, or maybe just rank, then is it like monotonic, like the bigger parameters I have for the multiplication tensor, I have the smaller it is? If I consider, can you hear me?
Yeah.
So if I consider matrix multiplication tensors with growing parameter, like the sizes of parameters, and I consider bigger and bigger parameters, does it behave monotonously? So that, for example, the bigger are those, the smaller is the rank?
You mean like by parameters, do you mean like the dimension of the matrix, or what
Yeah,
do
the
you mean?
MST.
Yeah, well, it's easy to see that when you take like MST and M to the K, S to the K, T to the K, right? Then it would behave monotonically. It's not that obvious that it will work like that for 3 by 3, it would get better than 2 by 2, but I think this is also for the asymptotic case. Yes, it is the case.
Okay. Thanks.
Okay. All right, so here we are. So I've told you about the Kronecker product and the asymptotic rank, okay? And I've told you about the Schoenhager thing, and the Schoenhager thing also works with asymptotic rank. So if you have a bound on the asymptotic rank of this thing, then you also get a bound on omega, which is actually like the limit of and as n go to infinity of this thing. All right, so then what I haven't told you about is the laser method here, which relates tensor powers of some tensor t with direct sums of matrix multiplication tensors. So this is what we're going to talk about in the majority of the talk from now on. So here's an overview. So the laser method uses some special structure, which I need to define, to reduce this problem here of computing direct sums to the problem of computing at the nth power. And it does it for very large k's, m's, s, and t. And they're functions of this power of n. So what you do is you have some huge power n you get to pick, and you show bounds on the rank of direct sums of matrix multiplications tensors, where k, the number of tensors, m, s, and t are functions of n. So you express them as functions of n, and then you do it by zeroing out variables in here, and you show that given a tensor of a nice structure, you can zero out enough variables so that you can get something of this form. And you have to bound how large m, s, and t are in terms of n, and how large k is, and then you get a bound on the rank here. But the rank here is at most little r to the n. So in order to get, basically you have to take the 1 over nth power, because it's the asymptotic rank, you get this. All right, so let's talk about the special structure of tensors that we want to talk about. So this slide is not going to be very special, but will get us to the special structure. So let's start with a tensor t. It's trilinear polynomial, and what we're going to do is we're going to take the variable sets x, y, and z, and we're going to split them very cleverly, let's say, into parts. So x is split into x1 up to x sub l. The y variables are split from y1 to y sub l. Some l is some constant, and the z variables are split into l subsets as well. Okay, so we have just partitioned the variable sets, and then given this partitioning, we can now define subtensors of t. So the ijk subtensor just collects those terms x, a, y, b, z, c, so that a lies in the ith part here, y sub b lies in the jth part here, and z sub c lies in the kth part over here, right? So it's just the sums of the things that lie in the particular subsets that we've chosen. Then, pretty trivially, we get that the tensor t is just the sum of these t sub ijk's. Okay. So we've just chosen some clever partitioning of the x, y, and z variables and expressed t as the sum of tijk's, where tijk is just those triples over here whose x variables lie in x sub I, y variables lie in y sub j, and the z variables lie in z sub k. All right. This applies to any tensor. You can apply any sort of partitioning of the variables and you'll get this. Why is this interesting? Well, if you happen to pick this partitioning in a nice way, and if you can get the tijk's are all matrix multiplication tensors. And then you will get t, the tensor t that you want, as a sum of the matrix multiplication tensors. Then your goal will be to get rid of some of these matrix multiplications tensors, so that what you end up is with a direct sum. And then you will have what we want. You'll have that you can zero out the tensor t into a direct sum of matrix multiplication tensor. Now I want to point out that any tensor t can be expressed as just a sum of matrix multiplication tensors, just because you can take the trivial partitioning, partition x into one element sets here of variables, and y into one element sets, and z into one element sets, and all these tijk's will be just scalar multiplications. And then of course you will get t is the sum of matrix multiplication tensors, namely scalar multiplications. what we want is these tijk's that you get by the partitioning to be actually bigger matrix multiplication tensors than scalars. And it turns out that for some interesting tensors, you can do this nicely. Okay. So here's an example. This is the Coppersmith-Winograd tensor. So it's parameterized by some value q, and q is usually 5 or 6, depending on which algorithm you use. And it looks like this. So you have q plus 2x variables. They go from x sub 0 to x sub q plus 1 over here. There's q plus 2y variables and q plus 2z variables. All right, what's nice about this tensor is that its asymptotic rank is actually q plus 2, which is exactly the number of x, y, or z variables. So in a sense, it's an optimal tensor. If you think of the rank, asymptotic rank as, you know, in terms of the output, right? So this tensor, now we can partition it. So the way we partition it is it would take the q plus 2x variables and put x sub 0 by itself in the set x sub 0. Put x1 up to xq into x sub 1, and put xq plus 1 by itself into x2. Do the same with the y variables, and do the same with the z variables. It's symmetric, so you do the same thing. And now, let's look at the t sub ijk's as I defined them as before. T sub 002 is only this term over here. T sub 020 is this term. T sub 200 is this term. T sub 011 is the sum over I of x0, yi, zi. 101 is the sum over I of xi, y0, zi. And T110 is sum over I of xi, yi, z0. These guys over here are just scalar multiplications. The output is the product of two scalars. Same here. The output is the sum of two scalar multiplications, and same here. It's 1 by 1 by 1. Over here, there's q outputs, z sub I from 1 to q, and they are obtained by the product of two scalars. So it's a 1 by 1 by q matrix multiplication. This one is a q by 1 by 1, and this one is a 1 by q by 1. So all of these are matrix multiplication tensors, and it's a sum. Okay, and these are actually non-trivial. They're not scalars. All right. Good. So this is like a scalar times a vector. This is a vector times a scalar, and this is an inner product. Okay, so now that we have that, the laser method, what does it do? It actually takes a huge tensor power. So T is some constant size tensor, and you partitioned it so that the tijk's you got are matrix products. Then you take the nth power of this tensor, which is, you just express it. What is it? So T is a sum of tijk's. You take the nth power. What you get is a sum of n, so products of n tuples. T1 tensor T2 tensor Tn, where these n tuples, you pick each one of them from tijk. So each one gets to be a tijk, and there's n tuples of tijk. So the sum of all possible of n tuple products of n tuples of tijk's here. That's what you get. Okay, pretty simple so far. The point is, you took the nth power and you get the sum of terms, but every term is a tensor product of matrix multiplication tensors. So actually, every one of these green terms over here is actually a matrix multiplication tensor. So the nth power of T also is a sum of matrix multiplication tensors. Now this is a very huge thing. And what we're going to try to do is cleverly choose parts to zero out. So what we get is actually a direct sum. So matrix multiplication tensors that don't share variables. So let's see how we would do that. So let's look at every one of these terms here. So it's an n tuple of choices where each T sub L, is something like tijk. And every one of these corresponds to a distribution alpha of the tijk's. What is the distribution? It is the fraction of times in here that you actually selected Tijk. So alpha ijk for every ijk is the fraction of times, and here you pick Tijk, right? So if T002, let's say, appears once over here, then it'll be a 1 over n fraction of the times you have T001. Okay, so every one of these corresponds to some distribution. And if you look at the set of these n tuples over here that correspond to the same distribution, they're actually matrix products of the same dimension. Because if you take A, B, C matrix multiplication to the tth power and multiply it by PQR to the uth power, no matter how you interleave these, you will still get an isomorphic. It will be isomorphic to the matrix product with the product of the dimensions. So if I had T copies of this and U copies of this somewhere in here, then there'll be, when you tensor them together, you will get the same matrix multiplication tensors. Okay. So if we have some distribution over all the ijk's, then it will define dimensions of the matrix product that these terms correspond to. Questions here? So, in other words, we can group these terms over here according to the distribution of the Tijk's for them, and every group will correspond to the same matrix product. All right. Now, what is our goal? Okay, so here's what I said again. Every one of these terms whose distribution is alpha will have the same dimensions, m sub alpha, n sub alpha, t sub alpha for some values of m sub alpha, n sub alpha, and t sub alpha. And our goal is to pick some distribution alpha and zero out variables in the nth power to get a direct sum of subtensors that correspond to alpha. And they will have the same dimensions by what we said up there. Okay, if we manage to do this, and what remains are L subtensors in the direct sum, then we can use Schoenhagen's theorem, plug stuff in, and we get omega is at most 3 log base rank of t to the nth power divided by L, divided by log base m sub alpha, n sub alpha, t sub alpha for that alpha. And if you look at this, in order to minimize omega, we want L to be as large as possible. So when you fix alpha and you fix m sub alpha, n sub alpha, and t sub alpha, you want L to be as large as possible in terms of alpha. Okay. And so we need to bound what L is for each choice of alpha. And then we also need to figure out what variables to zero out in order to get that L. All right. That's our goal. So here we are back in this picture. What we're doing is we took T, we partitioned it into these subtensors that are matrix multiplication tensors. You took the nth power. We got the sum of products, which are matrix multiplication tensors. We're picking a distribution alpha for the fraction of times each Tijk appears in here. And we want to get zero out variables to get a direct sum of some L subtensors that all correspond to alpha. So they all have the same dimensions, and then we can bound omega like this. So our goal is to figure out how to zero out stuff, to bound L, and to pick the best alpha. Yeah, somebody has a question.
Yeah, so my question is there a specific reason why you're picking them to be exactly of the same type subtensors? I mean, there are two explanations. Either it doesn't make sense because always picking the same size wins, or it's just unmanageable to analyze. So which one of those is?
Is the first one. So
okay.
Actually, if you have them have different sizes, you can actually always make it be. You get
So it's like a convexity argument.
Yeah, it's a convexity argument. Yeah, good. It's a good question. But yeah, it turns so Schoenhagen's theorem would work even with arbitrary. They don't have to have the same dimensions, but it turns out for our application, the best thing you can do is just have them the same. Okay. So yeah, so now we have to figure out what L, M sub alpha, N sub alpha, T sub alpha are as functions of alpha and N and T. All right, so it's like some optimization problem. So we're going to face a problem here, okay? So we define this distribution, which is a distribution over the triples, ijk. However, we plan to zero out variables and not triples of variables. And we'll have an issue. So we won't be able to necessarily pick the distribution that we want, because what we have a choice over is which variables to zero out, which only gives us one part of it. So we'll deal with this in a second. All right. The way we deal with it is like this. So we're going to define the marginals of the distribution. Namely, let's look at the x marginals. So for every I, which you recall is like corresponds to the x sub I portion of the partitioned variable set. So alpha sub I is just the sum over j and k of alpha sub I j k. So you just sum up for all possible choices of j, k, and you get the marginal over I. So this is just the fraction of times in this product that you actually use the subtensor, that one of these parts in the product corresponded to something that had an I in the first part. You don't care what the other two are. Okay, so this is alpha sub I. You can do the same with the y marginals and the z variables. Okay, and then you think about what the variable sets of t to the nth power are. Remember this t to the nth power, its variables are n tuples of the x variables, n tuples of the y variables, and n tuples of the z variables. And the original variables x, y, and z, those sets were partitioned into parts. x1 up to xl, y1 up to yl, and z1 up to zl. So actually you get, you inherit the partitioning of the variables and the nth power as well. So the variable sets, for example, over here in x to the nth power, the nth tuples, they're actually partitioned into these sets, where you pick a part of the original tensor, x sub c1 times a part of the, so you take n tuples of the original parts, x parts of the tensor. So you get a partitioning of the nth power of the tensor according to the partitioning of the original tensor. So then every subtensor, that green subtensor in the big sum that we got, that corresponds to a particular distribution alpha, it uses x variables that come from a part like this, with x sub c1 up to x to cn, where the fraction of times you picked x sub cp to be equal to I is actually alpha I times n. So the marginals, once we fix the marginals of alpha, we will get some x variable sets, right? There will be exactly those x variable sets for which in here you picked I, alpha I times n times, alpha I fraction of the times. You pick j, alpha j fraction of, and so on. So the marginals define variables that we care about. So what the laser method does is it picks some marginals, it sets the marginals to some value, and then it zeroes out all the variables in the nth power that do not have those marginals, right? So if I fix that alpha sub 1 is 0.9, then I will zero out all the variables that do not have 0.9n choices that fall in here, that fall in x sub 1 in each part. Okay. So I pick the marginals, and now I get to zero out the variables. And once you do that, you get a sum of terms that obey the marginals, right? And any term that corresponds to your desired distribution alpha does survive because it will obey the marginals. However, there might be some distributions that have the same marginals, and then the terms that correspond to those distributions will also survive. Okay. So then what the laser method does is after it picks the marginals, zeroes out variables that don't correspond to the marginals, and then it uses a different method to get a direct sum out of those. Okay, so any questions at this point? So here we go. We define the X marginals like this, as I said. This is what I just said earlier. So we get the variables are partitioned by basically these blocks over here. All right. And so I want to talk about how many possible terms in a direct sum you could possibly have. So let's pick the marginals, alpha sub 1 up to alpha sub L. The total number of variable sets that match these marginals is this multinomial coefficient. The number of ways you can split n into alpha n 1n parts that fall in x sub 1, alpha ln, alpha 2n parts that fall in x sub 2, and so up to alpha l times n parts that fall in x sub l. So this is the multinomial coefficient, and this is the total number of variable sets that could possibly match alpha sub I. And because when you have a set of disjoint subtensors, they cannot overlap on any x variable set, the total number of disjoint subtensors is at most this multinomial coefficient. So the number of subtensors you get is at most the number of variables. So the point is you cannot get more. And the laser method says that if certain conditions are met, you can actually basically get this value. So you can get a number of disjoint subtensors, so the direct sum that's actually equal to this value, which is the most you can get. So I want to mention what the conditions are. Okay. So what are the conditions? So we have defined the marginals. What we really want is a handle on the distribution alpha itself, because that defines the dimensions of the matrix products. But so the marginals, they define a linear system over alpha, basically by their definition. The X marginals are the sum over JK of alpha I JK, and the Y marginals and the Z marginals. So this is some linear system. The laser method will get the maximum possible thing, the multinomial coefficients, only if once you set the marginals, the linear system will give you what the distributions will be. So if this linear system has a unique solution, this is the only time it will give you what you want. And if otherwise, it will give something worse. So let me mention what that is. So otherwise, this linear system has multiple solutions, and it could be multiple distributions that are consistent with the marginals. Right. So as I said, we're zeroing out variables. We're not zeroing out triples of variables, so we cannot distinguish between different distributions that have the same marginals. So what the laser method does is actually it gives you a disjoint sum of M, which is the maximum thing, good subtensors, meaning those that actually are consistent with the distribution you want. But if there's other distribution, it will also give you some extra subtensors that are consistent with other distributions, consistent with the marginals, and those actually are not disjoint from what you have. They actually now interfere and are sharing variables with all the ones that you actually want to have. So in other words, it looks something like this. So you have a bunch of disjoint tensors, M of them, let's say. I meaning that the ith variable set differs from the jth variable set. So these are completely disjoint, I call them good, plus a bunch of other stuff. T1, 2, 3, that one shares variables with everything with T11, T22, T33, right? So you have a bunch of this other junk and it's interfering what you want. You want this, but you have a bunch of other stuff. If I happen to set a variable to 0 over here, I'll actually kill off 3 of these, which is not good. So now we need a way to get rid of these and have as much of this here as possible remaining. Okay. So when we do the analysis for matrix multiplication algorithms, getting rid of these guys here causes a significant penalty. And if we could just magically get rid of them without affecting the number of disjoint subtensors over here that we would get a much better bound on omega. But this actually causes a penalty. So here's the difference in what the laser method used to do and what we do. So suppose the laser method has these good subtensors that we want to keep. They're disjoint and they're matrix multiplication tensors. And there's some extra noise, which let's say S times is large. So you have M good subtensors and S times M extra subtensors. So we have to zero out more to get rid of the extra ones. And that reduces the number of good ones, as I mentioned. And the old approach showed that you can zero out all of these red ones so that M over S, this S over here, is good subtensors remain. And what we show is that actually you can get M over square root of S good subtensors remain. And S is typically quite large. So let's see how this affects omega. Right. So for omega, this is the bound we were getting. Is for a distribution alpha, you had the rank T of T to the nth divided by L. L is the number of disjoint subtensors we're getting. If L was M over S, then you put M over S here, and you get S up here, which is typically very large, affecting your bound on omega. Now we replace this S with a square root of S, so you get a lesser penalty. All right, so here's some more details on how it was done. So the laser method gives you these good ones and some bad ones, and you want to get rid of the bad ones. There's S times M of the bad ones. So the old approach, all it did was a greedy algorithm. It's the following greedy algorithm. You repeatedly take one of the good subtensors, and you can, because there's S times M extra subtensors, you can say that there is actually one of these good ones that shares order S, shares variables with order S of the bad ones. So pick one that shares order S of them, and then zero out a variable for every one of the tensors that it shares variables with. This will get rid of all of them, but it will also remove order S good subtensors, because each one of these shares a variable with one of the good ones. And so you remove all the ones that you keep one of the good ones, but you also get rid of about S of the good ones as well. So because of that, you get only M over S of the good ones remain. So you greedily kind of kill off stuff, but only give M over S in the end. So what we show is actually there's you can use the probabilistic method for this. You can show that actually if you pick M over square root of S good subtensors, then actually with non-zero probability, you will zero out all of these guys here. Just kill them off. So they're gone. And because of this, we show that there is a way to pick M over square root of S of these so that it works out. If there is a way, there's an algorithm. So we show the existence of an algorithm, and you can also get the algorithm if you think about it a little more. Right. So, and it turns out that M over square root of S is actually optimal for a large family of tensors. So for that family of tensors, you cannot do better than M over square root of S. There's no way to get more of the good subtensors to remain. Right. So that's all we do. So how useful is this? So it will always be useful if the marginals do not determine your distribution. And this happens for any slightly larger partitioning of the variable sets, because then the linear system will not have a unique solution. So And it definitely applies to all these powers of Koppersmith-Winograd beyond the 8th power, 8th, 16th, 32nd, and so on. So you can immediately apply the same analysis. You don't have to do anything new, and you immediately improve omega. So that's what we did. We took like the Gauss code for the 32nd power, and we just plugged in square root wherever S was, and then you can get the bound. Yep, there's a question.
So how large is the Q in like the optimal?
The Q?
The Q, the size, the actual parameter of the Koppersmith-Winograd
Usually
tensor.
it's 5, sometimes it's 6, but in the last, yeah, it's been 5, last several papers. Yeah, it's a good question. Like it would be nice if it's smaller, but that's where we are. So anyway, so now if you take any future tensor and you get your partitioning and it's bigger than like 3 sets per variable set, then you can just apply this and you'll get an improved bound. It's optimal for a large class of tensors. Interestingly enough, we were not able to show that it's optimal for Koppersmith-Winograd, but it is optimal for Koppersmith-Winograd-like tensors. So it would still be nice to show that it's up. I believe it should be. So, all right. So you can, the laser method has other applications, and maybe one could look into whether what we did has anything to do with the other applications. Okay, so what's next? So there has been this recent line of work that we've also been doing on trying to prove barriers for Koppersmith-Winograd-like tensors and beyond. And so, for example, you can define a generalization of the laser method that applies, there's various generalizations. So the first paper in 2015 showed that a certain generalization of the laser method applied to this particular tensor, the Q here is 5, the 5th Koppersmith-Winograd tensor to the 32nd power, you will not be able to beat 2.3725. So unless you do something slightly different than the laser method, then you won't beat this. But then you can generalize it even more. What if you depart from the laser method much more than this generalization? Then we showed that none of these Koppersmith-Winograd-like tensors will be able to beat 2.18. So we won't be able to go beyond that. Though I would love to get there, so that would be nice. Okay, so in order to get a bigger improvement than this, maybe you should try some very different sort of tensor, very different from Koppersmith-Winograd. There's the line of work with tensors coming from group algebras. Unfortunately, they also suffer from limitations like this. So maybe you need something completely different. Like we've tried a lot of tensors, and Koppersmith-Winograd, it seems to do the best, at least with the methods that we have so far. So actually what we really think should happen is we have to develop a much better method than the laser method. But as I mentioned, if you want to get omega equals 2, Josh showed that for a large class of tensors, the laser method is basically what you have to do. So maybe we need to find some completely different tensor and completely different method, and then maybe things. Or maybe omega is not 2. So that's another possibility. Why not? So that's it. Thanks.